So this video is going to talk about how to incorporate work by non-conservative forces. Alright, so this is conservation of energy, the method we're going to use to solve this, but energy is not going to be conserved. In fact, I'm going to lose some due to work by a non-conservative force. So the question is, what is the final velocity of a car? Alright, my car is 1,000 kilograms, which is red light for a car, but whatever. It's traveling at 3 meters per second. I can see the arrows pointing from left to right. And then a small braking force of 25 newtons is applied from right to left, and it's going to travel 30 meters distance. All right, so let's find out what the final velocity of the car is. The first thing I need to do is figure out with this non-conservative force of the brakes, um, what's going to happen. Is this going to add energy to the car, to the initial energy of the car, or is it going to remove energy from the initial energy of the car? To do that, I'll do something really simple. I'll take my finger on my left hand and I'll point it in the direction of the force, which in this case is the brake, so it's going to point that way. I'll take my finger on my right hand and point it in the direction of the displacement. And displacement goes from left to right because of the velocity arrow shows me that. So it's going to move like this. Since my two fingers go in opposite directions, it's going to remove energy from the start. So I'll start with summing up the energy on the left minus the work done by the brakes. And it's minus because, again, I have opposing directions between the force and the displacement, as my fingers can show. And that'll equal the final energy on the right. So when we're doing these problems, we're always going to add and subtract the work, which is the change in energy, due to each force in between our two locations. Great, let's go to the next step. So I'll do KE plus PE minus the work of the brakes again equals KE plus PE. And then I'll go through my usual set of questions, or the LOL graphs, and I'll ask myself, on the left, is it moving? Yes, so I'll keep that energy. On the left, is it above the other location's height? No, so I won't have any potential energy stored in gravity. I'll leave the work alone, and now I'll look on the right-hand side, the other location, and I'll ask the same questions. On the right, is it moving? I think so. I don't think it's stopped yet, so I'll keep that. On the right, is it above the other location's height? No, it's not, so I'm going to get rid of that energy. So this helps me to create the equation I need to figure out the answer. So I'll plug in my equations that I need. So 1/2 mv squared is the kinetic energy minus, and now instead of work of the brakes, I'm going to write the equation for brakes, which is the force of the brakes times distance. That's our basic equation for work, F parallel times d. And that's equal to 1/2 mv squared, and that v is going to be the final velocity. At this point, I'll put in my numbers and units. So 1/2 1,000 times 3 meters per second squared minus the force, 25 newtons, times the distance, 30 meters, equals 1/2 1,000 times v squared. And I'll isolate v, so I'll solve for the velocity. And when I do that to 3 sig figs, I get 2.74 meters per second.